Okay. I think we are ready to start, so please take a seat. Okay. Good morning and welcome from the Muon g-2 collaboration to the scientific seminar on the new results from the Muon g-2 experiment. In 2021, we released our first results on the measurement of the Muon g-2 based on 2018 data. Our results confirmed the predecessor Muon g-2 experiment at Brookhaven and showed at that time a more than 4 sigma difference with respect to the theory prediction compiled by the Theory Initiative in 2020. Today, we will present you our new results from 2019 and 2020, which consist of more than 4 times the data that we analyzed in our first result. The Muon g-2 is an international collaboration which is composed by more than 180 collaborators coming from 7 countries and 33 institutions. All these people have different skill and competence, but they work together to measure one single quantity, which is the Muon g-2, and you will hear today. In the Muon g-2 collaboration, what we are more proud are our younger colleagues, either graduate students, postdoc, junior researchers. These highly motivated and talented early career scientists are not only the blood, but also the driving force of our experiment. And I would like to thank them, really. Thank you. Let me also mention how important it has been for our collaboration to foster a highly welcoming and inclusive environment where each collaborator feels represented and brings their own unique contribution to the success of the experiment. And of course, I would like to thank all the collaboration. Okay, now, our experiment could not have been done without the generous support of the funding agency, which are listed here. And let me thank deeply, really, on behalf of the Muon collaboration, of the Muon g-2 collaboration. But equally important were the dedicated, passionate, and professional works by engineers, technicians, supporting staff from the collaborating institutions. And after thanking the funding agency, all the people who make the g-2 successful, and this today's seminar possible, and most important, you for being here, I will leave the floor to Brendan. Thank you.
Thanks, Graziano. So let me second everything Graziano said about all our collaborators and all the help we have there. Since we're at Fermilab, we just wanted to make a call out to some people here because, you know, this isn't the type of number where it takes a village. This is the type of number where it takes a lab. Okay, so we just want to thank all the engineers and techs who kept the ring on. This was a big thing. All the accelerator operators and experts who got the beam and helped us build and execute the experiment. So this is an experiment where the accelerator is actually the experiment. And we could not have done it without the accelerator division, not just providing beam, but coming over and helping us figure out what was going on and helping us do the experiment. To all the computing experts who bailed us out when we were drowning in data, this was multiple times, where the kids that keep going in and the lifeguards keep needing to pull us out. Computing division bailed us out numerous times. The safety experts who get us home and safe every day, the finance, all the communications people, all the business service people who keep everything going, and our admins who get us through every day no matter what the challenge. And I just want to make a special call out to 3 unsung heroes associated with this result today. The first is Raymond Lewis in ES&H, who got our experiment turned back on. The second is Corinne Vendetta in PPD Finance, who helped us get the money that we needed to do everything we're talking about today. And the third is LaToya Woods, who once we got things going was able to keep the wheels greased and keep things going. So thank you to all them. Thank you to everybody at Fermilab. We really appreciate it. Okay. And now let me bring out our analysis coordinator, James Mott, a Wilson Fellow at Fermilab, who will present our results to you. Come on out, James.
Hi, everybody. Hi, good morning, everybody. As Brendan said, my name is James Mott. I'm a scientist here at Fermilab. I'm the analysis coordinator for the last 2 years on the G-2 experiment, and it's my pleasure to tell you about this result. I don't think anyone is as happy as me that this thing is finished. I don't care what the number is, it's done. Right, so I thought I'd just start off. We're called Muon G-2, right? I've introduced me. Let's introduce the experiment as well. We'll go through Muon, and then we'll talk about what G-2 is as well. So muons are second-generation elementary particles, right? So up here on the top left, we've got the standard model particles. In the middle, we've got the second generation, and the muon sits right here. So it's pretty similar to an electron, but it's 200 times more massive, and it's unstable, right? So all that extra mass can be converted into energy, and it decays into an electron and a couple of neutrinos, or a positron and neutrinos. It's got quite a long lifetime, 2.2 microseconds for an elementary particle. It's not very long in kind of our lives, but it means that we can make these particles and we can manipulate them in the accelerator so we can actually put them to good use. It's got a Goldilocks mass, meaning that it's heavier than the electron. It's kind of as heavy as, so it's more sensitive to virtual particles and new physics, but it's just lighter than the pion. So it doesn't have any messy hadronic decays, and it's a nice clean system to work with. And the muon's got a property called spin, as do a lot of these particles, and that spin rotates when you put it inside a magnetic field, and that's what we leverage for our experiment. So the G in Muon G-2, that basically determines how the spin processes inside a magnetic field. So, you know, you've got a torque with this magnetic moment, and the magnetic moment is proportional to G here. So you put the muon inside a magnetic field here, and it starts to rotate around. Its spin starts to rotate like that. Okay, now if all that there was in the world was muons and photons, if this was the world we lived in, then G would be exactly equal to 2. That just comes straight from the Dirac equation. But we know that's not true, right? There's more particles than that in the world, and so there's these virtual particles that we are zipping in and around when we go through our magnet, and they interact with the muon with diagrams such as this one here. So this means that G is ever so slightly larger than 2. And in this diagram, I've just called these X and Y. These could be standard model particles that we know about already, or maybe they're also some new physics particles that we don't know about yet. Okay, so what actually is in the standard model component? So here's all the different categories that go in there, right? We've got the Dirac equation at the start, and then we've got QED, electroweak physics, and then these two hadronic terms at the end here. So all the values that I'm about to show you here, they've been compiled by a group called the Muon G-2 Theory Initiative, and we're very thankful to them for all the work they do in collecting together the theoretical inputs and providing us recommendations. There's just over 100 of them here, and here's a picture of them from 2018 in Mainz. So their last compilation actually came out in 2020, before our previous result that Graziano told you about, and there's a link to it here, and we'll talk a little bit about the values as the talk goes on. So here are the values from that. So if you just stare at these numbers here, you can see this one's really big compared to the others, and that's reflected in these pie charts over here. So the contribution here is shown on the left. That's basically just all red, right? It's all this QED term. But yet the error in there is really tiny, this little slim piece of this pie, because actually the error is completely dominated by these two hadronic terms on the right, and in particular the hadronic vacuum polarization, or HVP, which is this term here at the end. So that's basically, you've got a propagator here, photon propagator, this hadronic blob in the middle, and that's the loop that you're putting in there. Now you'll notice all the interesting physics here is in these loops, right? This is the bit we actually care about. And so instead of talking about G, we actually talk about A mu, which is G-2 over 2, right? It's basically this block here. And this G-2 here is the G-2 in Muon G-2. The other thing as well, so this A mu, you'll sometimes hear it called A mu, sometimes the muon magnetic anomaly, sometimes the anomalous magnetic moment. whenever we say all those things. We're talking about this A mu quantity, which is what we're trying to measure. Right, so you can take a step back and look at this and say, gee, actually, everything we know about physics is in here, and we need it to be in here. Otherwise, we wouldn't be able to get agreement. But then the natural question is asked, well, what happens if there is some physics we don't know about? Could we be sensitive to it in the same way that we're sensitive to everything we do know about? So this is the crux of the whole point of this work, right? The experiment and the theory. We calculate them both very precisely and measure precisely, and then we compare the two numbers, and we basically ask, is there some new physics in our experiment which isn't included in the standard model? Okay, so now I just want to hark back to 2021. As Graziano mentioned, this is when we put out our last result. So I just want to remind you of what happened at that time. So we had, before the result came out, this was the picture that we had, right? We had this experiment from Brookhaven, which put out its final result in 2004. And this disagreed with the standard model prediction over here at the tune of, 3 to 4 sigma over time. So that's over there on the right, and this is here. And then with our result back in April 2021, we put this point on the plot. And so this is actually only using 5% of our total data, but it was important because we confirmed this Brookhaven value in terms of we agreed with it over here. We didn't end up over here. Right? If you combine them and then take the average, this is the 4.2 sigma that Graziano mentioned earlier. So today, mostly, I'm going to be talking about the right-hand side of this plot. Right? I'm going to mostly be talking about what we're doing to improve the experimental side of things. But there has also been some movement on the theory, the standard model prediction side. So I'll just spend just a tiny bit of time here trying to explain what's going on there. Now, there is a summary that just came out yesterday from the Theory Initiative. It's on their website. It's going to do a much better job explaining all the details than I am today. If you're interested and want to know more about the theory, then this is a good starting place. It's like a 2-page document with everything that explains exactly where everything is right now. So that's at this link here. And if you do go through that, what you'll find is that most of the interesting stuff is going on here in this hadronic vacuum polarization term on the right. That's the one with the big error. So there were excellent talks last week, just 6 days ago on Friday, at Lattice 2023, which was here at the lab, on the different methods. That's another good place to go and look if you want to learn more about the theory. There was 2 different talks about the 2 different methods that we can use to calculate this term. So there was a talk from Alex on the dispersive approach, and one from Simon on lattice QCD. And so I'll just try and take, their hour of material in their seminar and condense it into 2 slides, and we'll see how that goes. So for the dispersive method, right, this is sometimes called the E plus E minus method too. Right, we basically rely on the fact that if we have this hadronic blob at the top, we can use analyticity and unitarity to cut this in half, flip it around, and what we find is we can relate that blob to a cross-section of, say, E plus E minus to hadrons. So you can write that out in terms of this equation up here on the top right. So what you find is it's an integral over energy. That's what this S is here. And where you've got some calculable function here divided by energy. And then this R ratio, right? This is the hadronic R ratio, which has been measured for many years. It's the ratio of this cross-section over some normalization. So to calculate this, you basically use the data from the different experiments over the last 20 years, and you plug it in here, and you integrate it up. Now, it's worth noting that because of this 1 over S term here, the low energy is weighted strongly, and 73% of this contribution comes from the lowest energy 2-pion channel, right, pi plus pi minus. So that's an important channel, and that's kind of where a lot of the activity has been going on here since the white paper. So if we hark back, this was kind of the situation here at the white paper. This is the contribution from that 2-pion channel here that I'm showing. So you have in the band here, this is one of the combinations that was included in the white paper. And here are some different measurements from different experiments down the side. So there's some tension here between Clary and Babar, which has been scrutinized and is still being looked at. But the error on the final combination was inflated to take into account that discrepancy. So that's already accounted for. But since then, we've had these 2 new results coming out, these sort of most important new results that have come out. So we've got 2 from a collider at Novosibirsk in Russia. There's the SND2K result, which is over here. That kind of agrees fairly well with the stuff that's already in the combination. But this CMD3 result, which came out in February this year, is clearly discrepant. Right? It's miles over here, and the other points are all over on the left side. So there's been a lot of scrutiny. It seems to be holding up. So this is a puzzle that we need to to study further and understand more. But all is not lost, right? There are more results coming out soon. In the time scale of a year to a couple of years, we expect more results from Babar, Chloe, S&D, BEST3, and a little bit longer, maybe BOL2 as well. So there's going to be more experimental input in here, which is hopefully going to resolve this problem. For lattice QCD, that's a different method altogether. It doesn't use data. It's first principles ab initio calculation done on the lattice. So those results weren't included in the white paper back in 2020. So this was the state of affairs at the time. So over here this is the dispersive calculation in gray. Here's the experimental result from run 1 here in orange. And you can see at this point, there were some values out here in terms of the lattice calculation, but their uncertainties are large, and they're not really providing anything in terms of, which of these is correct at this point. But that changed after 2021 when BMW's result was published. It was actually out a little bit before that, but published in 2021 after the white paper. And that puts this point here on the plot. So you can see now the uncertainty here is sort of comparable, at least, to the other uncertainties on there. And it's much closer over here to the experimental result in tension with the dispersive method. So other groups have been cross-checking this since that result came out. It's kind of a staged approach. The intermediate stages are agreeing, but as of yet, there are no full HVP calculations to the same precision from other groups for us to look at. So it's a waiting game here too, but there's a hive of activity going on. Okay, so that's all for the theory. I want to come back and focus for most of the rest of the talk on the experiment. So what data are we actually talking about here that we're analyzing? So this plot here is one that we like to show, showing our data over time. So this starts in 2018 and runs through to 2023 here, over our whole data collection period. So back in April 2021, we'd collected this much data. And this is important. It confirmed the Brookhaven result with a similar precision to what they had at Brookhaven. So since then, we collected more data in 2019 and 2020 before COVID shut us down in March 2020. So that's this run 2 and run 3 result. That's what I'm telling you about today, right? This is the data we're using today. It's got something like 5 times the statistics that we had in run 1, so we can beat down the statistical error. But that's not all. We've carried on taking data since then. And in March this year, we finally reached our proposal goal of 21 times the Brookhaven statistics. And so that's there. We've reached our full statistics. It's something like 4 times the data of 1, 2, 3 combined. So that's under analysis now as well, and we'll be coming at a later date. Okay, so how do we actually do this experiment? Well, here's the principle behind it. We take polarized muons, and we store them in a storage ring with a vertical magnetic field. Now, if you do that, right, the muon's going to go in there. Its spin is going to start to precess around inside the magnetic field, and it's also going to go round and around at the cyclotron frequency, right? It's going to go round in a circle, going around at the cyclotron frequency inside the field. Now, both of those are proportional to B, the magnetic field. And if you take the difference between them, what you find is you get this difference frequency, omega A. That's going to be important. So that one there is the difference between them. That's proportional to A mu, the thing we want to measure, some constants, and B, the magnetic field. Okay. So what we do, we put the muon inside. Here it is at the top. I've injected it in here. There's a momentum arrow in blue and a spin arrow in red. And what you'll see if we start it is that the spin arrow starts to creep ahead of the momentum arrow as we go around the ring. Right, so as you go round and around, the spin arrow is just getting slightly ahead of the momentum one, and it's going to have done one more circuit in a short while, right? Now, if you happen to, instead of just going around here, you just sat at one point in the ring and just watching what happens when you come by, instead you see these arrows, right? So every red arrow on the inside is lining up with the spin of the arrow as it goes around. But what you see instead is you see this difference frequency, which is much, much lower than the spin frequency. So the spin frequency is this one in the middle, and you can see it's going around much, much faster than this difference frequency, omega A, around the outside. So what we do is we set at each point in the ring, and we just measure this frequency as it goes in and out. That's our omega A. That's what we want to measure. So this is the crux of it. We measure that omega A. We measure the magnetic field. We take the ratio, and we then use that to extract A mu. Right, so that's the principle. What does it look like in real life? So here's a picture that you may have seen before many times. This is our storage ring over there. It's 14 meters, that's 50 feet across. It's got a 1.5 Tesla field. And so basically how it works, it's hard to see from here, right? But if you were to slice, say, down one of these white lines here and then look back in this direction, what you'd see is the C shape of the yolk looking like this. right? So there's a yoke there. This is a big chunk of iron. And then in here, this is where we put the muons. And then there's all sorts of components that are adjustable that we can move around to make the field as uniform as possible right here in this region. Then there's these superconducting coils. We run current through them in these directions. And if you stare at it and do your right-hand rule for long enough, you can convince yourself that there's a magnetic field that's going to go around here, and it's going to come up and be vertical in the muon storage region. Now, we want to measure the B field very precisely because we're going to use it in the ratio to measure something precisely. So we measure that using nuclear magnetic resonance, NMR probes. And we primarily use a trolley to do that, right? So there's this trolley that looks like this. It's like a really long Coke can, Red Bull can or something. It's got 17 probes with petroleum jelly that are sat around at the top here. And we move it around the ring. We can't do it when the muons are there, right? If we put this in and then put the muons in, then the muons just scatter off it and we lose all the muons. So we can only do it, say, every 3 days when we're not taking data. And we make these maps like this one here. There's 8,000 of these maps every time we go around the ring. And then what we really care about is the azimuthal average of these, right? The muons are going around and around and around, sampling the whole field all around there. So we look at the azimuthal average of that, and it looks something like this. So in general, the variation is less than 1 ppm, and even better than that in the middle where most of the muons are. There's some around the edge here. It's a bit harder to keep uniform, but there's no muons there. So that's all well and good. We've measured it every 3 days, but we didn't have any muons in while we were measuring it. So we need to know what was going on when the muons were there. So we do that with these 378 fixed probes, which sit above and below the ring, right? So that's what these orange and blue dots are representing. Each one of those is a probe. And the idea here is that we anchor those measurements at the trolley runs at either end, and then we use these fixed probes to monitor what's happening to the field in between. So if you imagine we didn't have the fixed probes and we just had to draw a straight line between these trolley runs, then we're going to miss all this structure of going down. So this is why we have to capture, say, this dip is caught by the fixed probes. We know that that's what the field was doing when the muons are in there. Now, so far, we've measured the magnetic field with petroleum jelly frequencies, but we need to relate it back to something that we can use more precise measurements from other people to relate to the actual field. So we do that with water in a plunging probe. And the way this works is it's a probe that's on an arm that can go in and out of the storage region. And what we do is we put the trolley in place, take a measurement of the field there, move the trolley back and swap it with a calibration probe, take that measurement, and we keep swapping back and forth, and we keep going until we've transferred the frequency calibration from the trolley probes to this plunging probe. Then we pull that probe out and take it over to argon, where we have an MRI magnet with a very uniform field, and we then check that against this spherical water probe, which is shown here. That gives us our final calibration to go to a magnetic field. Now, both of these are also cross-checked against a helium-3 probe, which has different systematics, and they agree. Okay, so that's the field. We'll come back to this plot. So we've measured the field, but we don't have any muons. So we should put some muons in there. So as Brendan was saying, there's a huge amount of effort from Accelerator Division, the whole complex, the whole lab, to provide us these muons. I'm not going to tell you where they come from today and how that all works. I don't have time. We can just assume they come out as if by magic out of this hole in the wall and come down here. So we've got our magic source of muons coming through here. They go around, they curve in our magnetic field, right? They start to go around this cyclotron motion. Now, if you do that and you put them in, they're just going to go around in a circle, right? It's just a vertical B field. They're just going to go around in a circle, and they're going to come and clatter straight back into the wall where they came through, right? There's a whole injection hole here. It's going to come back around, and we're going to bang straight back in where we came. We don't want that. So what we do instead is we play this trick where they get to about 3 o'clock here, we change the magnetic field slightly reduced, right, by a really small amount, and it's just enough to rotate this so that you go down and end up in the center. So we do that with this kicker magnet. So you can see now we've rotated it around and we've ended up back in the center. And that's basically these long plates where we run a load of current through to make a magnetic field. The aim of the game is to get the current high and fast, right? We want to get it high so we get a magnetic field that's large enough, but we want to make it super fast so by the time the muons come around again, it's gone, right? So the idea, it kind of goes up and down in 150 nanoseconds or something. Okay, so now we've got these muons. They're going around inside our storage ring, but we haven't done anything about up-down motion yet, right? So they're just going to fly up and out of the storage ring or down and out of the storage ring. So we need to contain them vertically, and we do that with these electrostatic quadrupole plates. So there's 4 stations of those at these points around the ring, and they just look like this, right? They're just 4 plates that we put high voltage on, and the idea is we squeeze the muons vertically to keep them contained. Now, so the muons are in there, they're contained, but we can't see them yet. So we have to wait for them to decay before we can detect them. So the way this works is we measure their decay positrons. Now, they've got lower momentum because there was also neutrinos given off, and so they're going to curl inwards in the magnetic field towards the inside of the ring, which is instrumented with all these detectors. So there's two main systems. The first system is the tracker. The first system I'm going to tell you about is the trackers, right? So there's two of those. There's one here and one here. And we use these to kind of back project and say, where did that muon come from? And it tells us about the muon distribution inside the ring. So I'll show you a video of that in a second, but before I just wanted to orientate you. So here's the radial position here, here's the vertical position, and the color is the intensity, right? And this is basically, if you were to stand there and look at the muons as they're going past the tracker, this is what you see, right? But this is real data coming from the tracker. So as we start it, you can see the beam oscillates backwards and forwards. This is to do with those quadrupole storage fields, right? So the beam is oscillating backwards and forwards like that, and it's also oscillating up and down here. It's kind of breathing up and down. You can see if you squint as well. So you can see this is really rich source of information, right? It's telling us everything there is to know about the beam. It's all in here. And so we use all this information to do beam dynamics corrections. We tune the simulations with it, and we also optimize the experiment while it's running using some of this data. The other main function for the tracker is to be able to tell the magnetic field map where the muons are, right? I said before, we don't care about this stuff around the outside because there's no muons there, and sure enough, there's no muons around the outside here. So what we do is we collapse this down over all time, and we get something like this heat plot, and then we use that to weight the magnetic field map, which are these contours here shown on top. Okay, so the other detector system that we have, this is the real workhorse of the experiment of these calorimeters, and there's 24 of them around the inside of the ring, like this. So we use these to measure the omega A precession frequency. Now that works due to parity violation. So as the spin is pointing in the direction of the momentum, what you find here, so this is the energy spectrum here on the right, on the left, sorry. So the energy spectrum rocks back and forwards as the muon spin and momentum are aligning. So when it's back now, this pointing away from it, and then now it's pointing in the same direction as the momentum, and then back and forwards, right? So what you can do is a simple experiment. It's like a cut and count, right? You cut and then count the stuff above your threshold, and what you find if you do that over time is it looks like this. So this is just the same number of muons in these two hatched areas here. So on the right, this is the time spectrum, and this oscillation as it goes up and down, that's oscillating at omega A. So we basically do this count and then grab this data and extract the frequency from there. So here's a lot more of that data, right? That was real data on the last slide, but this is a lot more than just the first couple of oscillations. This is all of them. So this plot's a wraparound plot, so it starts at the top here and then wraps around and then keeps going down instead of trying to go all the way out on the x-axis here. So the black points are data and the red points are fit. We basically do this fit and extract omega A. You can't see it on this scale because the statistics are so high and the effects are low, but there are also other things apart from just this straight oscillation that we need to add in here. We need to add beam oscillations. As the beam is swimming back and forth that we just saw, when it's closer to the detector, we see more. When it's further away from the detector, we see less. So this number you're going to see is also going to go up and down at that frequency too. So we deal with all those beam oscillations, and then we also have to deal with muon losses, where the muons are lost from the ring before they have a chance to decay and end up in our plot. So when you do that, you can put them in, you get a good chi-squared, and you get an unbiased extraction of the frequency. Okay, so that's kind of the basics of it. Now, it's slightly more complicated, so I just want to spend one slide saying, this is the real world we live in. And we need to make these 7 small corrections. So the idea here is we're trying to measure this ratio, right, the omega A over this field frequency, omega P. We actually measure some frequencies which aren't these true ones, and we need to correct for a load of different effects here, just these 7. They're all small, to get the right answer. So the first ones we've got here are, we call them the electric field and the pitch correction. And this is basically saying that the simplified picture we had, if instead of just having the vertical B field, you put electric fields in, then you reduce the magnetic field, the muons see. And the fact that muons are going up and down inside the field as well also reduces the field they see a little bit. So these are corrections we have to make. Over here, these are kind of experimental measurement issues, right? These are ones where the phase of that plot changes over the course of the fill. A changing phase versus time is frequency, right? So If you have a changing phase, then you have a different frequency, so we need to correct for those effects. And then at the bottom here, these are two magnetic field transients, which are basically fields that are present when we put the muons inside the ring, but aren't present on average when we take all our NMR measurements asynchronously. Right? So they come from the quads that we only pulse when we put the muons in there, and from the kicker, which we only pulse when we're injecting. Now, this looks kind of daunting, a load of corrections, but most of them we designed out of the experiment in the first place, right? So they're small, they're basically small, right? So the total correction of these is 622 parts per billion, and that's dominated by these first two, this E-field and pitch, which have been known for a long time, and it's spin dynamics, and there's not too much uncertainty associated with them. Now, having said the corrections are small, we're trying to make a very precise measurement here, so we can end up with uncertainties from these corrections, which are kind of large. And that's sort of what happened in run one. So let's take a look at the run one uncertainties and start asking where we might want to improve this time around. So up here on the top left is a pie chart showing statistical and systematic uncertainties. The total was 460 parts per billion, and it was just dominated by statistics, right? 434 there. The systematics were still sizable, 157, and if we break that down over on the right-hand side, you can see in this pie chart that it's dominated by a couple of terms. There's this quad transient field here, and this phase acceptance correction up here. So we'll have a look at why they've got smaller going forward in the next few slides. So in general, we can think about the different categories we've got for improving in this measurement, right? And I've sort of broken them down into four here. There's statistics, running conditions, more measurements, and analysis improvements. And we'll go through these, and I'll explain to you what these plots are as we get to them. So the first one's going to be statistics. This is kind of easy to understand. We ran for a lot longer, took a lot more data. It was hard work, but it kind of guaranteed payoff in the statistics at the end. So here's run one. This axis is basically the same as before, except that this is now the positrons that made it through all our data quality, weren't systematic studies, everything's good, and then we put them in our plot at the end. So that's why this is a slightly different axis here. In run 2, 3 here, we've got something like 5 times as much data as over here, and when you plug those in, and you can then figure out the statistical error here, which is shown on this axis and in black. So you start off and the statistical error comes down very quickly. Right? You didn't have any information, now you've got some information, so you come down quickly. And life's getting harder and harder as we go on, but we are still falling down as we take more of this data. So, we said 430 for run 1. We're at 201 now for this run 2, 3 analysis. And if we combine both of them, they're at 185 parts per billion. Is the precision, the statistical precision of this result. Okay, second one's running conditions. Now, in run 1, we were still figuring out how to make this thing run like we wanted it to, and we had some issues which we had to deal with in analysis and inflate some uncertainties. So one of the main ones that we had in run 1 that was a problem was we had these damaged resistors in the electrostatic quadrupole systems. So there's 32 plates. 2 of them had resistors. They still kind of worked, but they were just not quite the resistance we thought they were, and they've changed the time constant for the charging of the plates, which led to unstable beam storage. So we figured this out at the end of run 1, redesigned the resistors so they stopped breaking, and then replaced them before run 2. So all the problems that were associated with that just vanished because we fixed the underlying root cause. So you can see some sort of effects here. So this is the vertical beam width over time. In run 1 is shown in black, and then this is run 3 data shown in red here. You can see it was changing a lot over the course of when we were trying to take the measurement. Now it's not changing anywhere near as much. And this directly translates to this phase change on the right, where it was changing a lot during run 1. It's not really changing at all. And remember, changing phase is very bad news if you're trying to measure a frequency. So by basically wiping out this effect, we reduced the uncertainty on this phase acceptance effect to be 75 ppb in run 1, and it went down to 13 now. Right, so it was a big chunk on the pie chart. It's much smaller now. As an aside as well, the beam oscillation frequencies that we use are stable too. Right, the quads have stopped changing during the measurement, so that makes life a lot easier as well. Right, the second running condition improvement here is Hall temperature. So you want the temperature in the Hall to be stable, right? Because as it changes, the magnet heats up at different rates, depending on what it is. And so it changes shape very subtly, and that distorts the magnetic field. So you don't want to be having to deal with a magnetic field that's shifting all the time. It makes the measurements of everything much harder and everything else, right? So the big improvements here, there's two, one from run 1 to run 2 and run 2 to run 3. You can't really see the one from run 1 to run 2, but if I zoom in, you can. So up here, you can see before in run 1, we had this day-night oscillation as the hall would heat up and cool down. So we added insulation. So this was the picture before. We put this cladding all over it, which is what you'll see now in the updated pictures of it. And so that happened between run 1 and run 2, and then it's very flat. This is the same time range over the top. You can see there's no oscillations there. And then from run 2, run 3, that's really striking, right? We stopped losing control of the hall temperature here because we improved the hall cooling. So before we were increasing temperature, the outside temperature was warming up over the months, but now it's flat. Okay, so the final upgrade that we made to the running conditions was to improve the kicker. So you remember that's the magnet that we use to injection to make sure the beam lands on the right orbit. So at the end of run 2, 3, for the last 18% of this data, we have this upgraded, stronger kicker. The muon distribution depends on that kick strength. So what I'm showing here is the momentum distribution of the stored muons. In the black, you had it how it was before the kicker upgrade, and then in the red is after the kicker upgrade. So you want it to be ideally centered on 0 with no width at all. So we've centered it on 0 here, and we've narrowed down the width slightly as well. And this leads to a lower electric field correction in the end. So we've reduced one of the corrections down to where we wanted it in the design. And finally, we do a much better job of matching the injection phase space with our storage phase space for the beam, which means that the beam oscillations that you saw in that plot where they're wiggling back and forth, right? Those oscillations here, this is the mean radial position versus time, right? There's those oscillations showing up. In black was before the kicker upgrade, in red's after. They've shifted closer to the middle, and they've shrunk down as well. Right? So that's what we want. Okay, so the third category for improvements is measurements. This is another one where there was some large improvements here. So the largest uncertainty for the run 1 analysis was actually this quad transient field. So what happens here, right? We pulse the quads every time we put muons in the ring. So we put electrostatic forces on them, and then we take them off. Electrostatic forces on, take them off. And that makes the quads vibrate, right? And so now you've got these vibrating plates inside a magnetic field. They're going to generate eddy currents in their own magnetic field. And sure enough, that's what we see. So this is a plot here showing the field change versus time. Every one of these gray bars is muon fill, right? So that's us putting muons in the ring. So you can see we sort of kick it off. It starts oscillating in some free superposition of vibration patterns. Then we give it another kick when we injected the next muons in, and it goes on and on and on like this. And so this is the pattern that we want to measure. You can't just put our NMR probes inside the quads because they're metal and it will spark, and it's not a good idea. So we had to make a new probe to do this, housing it in insulator. Now, time we'd made the new probe and done the analysis, we just didn't have that much time to make all the measurements we wanted to for run 1. So we actually only ended up making them a few measurements around the ring. So this is the azimuth around the ring here. It's kind of taking the ring and flattening it out on the page. You've got the different quad stations shown in green, right? The electrostatic quad station shown in green here. And the gray bars show that, we measured a few places in Q3, not many places in the others. And we found that there was variation between them that just didn't make us comfortable enough to just take these and extrapolate around the ring or anything. So instead, we conservatively put a 92 part per billion systematic on this. Now, going forward in run 2, 3, well, after run 2, 3, but for the analysis here, we put it on a trolley trail. So, the trolley goes around inside the ring. There's rails there for that. We built a housing for the probe so they can do it as well. And so that means that we can then map fully around the ring. Instead of just these points, we've now got all these blue measurements. So you can see we've fully mapped out all these quad stations now. And so we've gone from basically not having much knowledge at all about what was going on here to having really, really fine, detailed knowledge about it. And it means that our uncertainties come down by a factor of 4 to 20 parts per billion here. There's one other transient field that we've done improved with measurements. This is from the kicker. We also fire the kicker once. It makes eddy currents in all the metal around it. And they then fade away and make this transient magnetic field. I won't go into great detail here. We measure it with a Faraday magnetometer, and basically the problem we had before was there was a lot of vibrations in the optical fibers and the whole system, right? When every time you fire the kicker, everything vibrates a little bit, and it made it hard to disentangle what's real field change from what's just vibration in the optical fibers. So we improved all that, and now we've gone from this black line where you see all this up, down, and everything else around here to this red, which is much cleaner. So that uncertainty now has come down from 37 to 13. Okay, so the final improvements, I'll just show really quickly, are analysis improvements. So these there's sort of two main categories. It's hard for me to describe to you without giving you a whole seminar about how the analysis works in the first place. So I'll just give you a real rough flavor for them. So the first one's pile up, right? This is the same as pile up everywhere else. Two things arrive at the same time and look like one thing, right? The calorimeter lights up with energy. You can't tell whether there was two things going in there or just one. And that can end up biasing omega ray. So we improve this in two different ways. The first one is by improving the reconstruction algorithms. So we just did a better job of separating them out. The second one is the way we actually correct for this statistically. We improved all those algorithms too. So we kind of went at this from a two-pronged approach. And you can see over in this plot here, this is the energy scale. This is the energy on the x-axis. This is the energy spectrum that we see in our calorimeters. It's a log scale here. And everything above the decay endpoint here, this is all pile-up, right? This is multiple positrons showing up at once. The same data run through with the two different clustering algorithms. And you can see going from the old clustering in black to the new clustering in red, it's reduced by a factor of 5 or something just by doing a better job with the clustering. So that reduced the whole effect down. The final one is the E-field correction. As I said before, this depends on the Muon momentum distribution. And before, we were assuming that the momentum distribution we store was the same no matter where in the injection bunch you lie, right? We have some bunch that comes in with some width, and we were saying, no matter where you are, we store the same momentum, which was an approximation. So now instead, we take some correlations. You can see this is the injection time here and the momentum. You can see they're just ticking up a little bit here. There's a little bit of a smile here. And now we take that into account instead. We knew about it before. We had a larger uncertainty for that to cover ourselves. Now we make the correction and reduce the uncertainty. OK, so that's all the analysis improvements. So we can start staring at the final summary tables for these things. So we've got everywhere, if you look here, so this is uncertainty on the x-axis and the different categories here in the plot, and the equation, sorry, are shown on the left here. So everywhere, going from run 1 in red to run 2, 3 in blue, it's reduced everywhere, right? The different categories right up the top here, these are the analysis improvements I just told you about. This big drop here is for the damage resistors. That's the phase acceptance. We've got also big drops here from improved measurements in the quad transients and the kicker transients. So most of the places where we really beat down these systematics, I've explained to you where they came from. And now, once this is the final sort of distribution of systematics, we're now getting to the point where they're coming from multiple sources, right? There's no longer one that's dominant. This omega P systematic here is actually broken down into like a handful of 20 or 30 ppb ones as well. So it's not like there's one big dominant one with low-hanging fruit left now to deal with the systematics. We can maybe reduce more, but we're getting to the point where we can't go too much lower in systematics-wise, I think. Right, so what are all these numbers? So here are the final values. This is from the paper. This is the table. So the total uncertainty at the end of the day for this run 2-3 is 215 parts per billion. And so if we now try and do some comparisons with run 1 here, we'll put this table and fill it in. So statistical run 1, we were 434. Now we're up here at 201. That's a big drop. And then for systematics, we've gone from 157 now to 70 parts per billion here. So both of those gone down by a factor of 2.2. Nearly equal improvement in both, so we're still statistically dominated. If you take that pie chart from before, it just shrinks down, right? The proportions are the same. Now, what I really want to show is the fanfare here is this 70 parts per billion number. For us, this is a huge achievement, right? Our proposal goal was 100 parts per billion, and with this result, we've really surpassed it by quite a long way, and we've hit 70 parts per billion here. So this is a real achievement for us, and for me, at least, this is the real milestone of this result, is that we've actually made our systematics goal. Okay, so before we get to the final result, let's just talk about blinding. So we do the analysis blind to avoid bias. There's software blinding and hardware blinding. The hardware blinding is kind of our real fail-safe at the end of the day. And we do that by altering our clock frequency. So we get some esteemed members of the directorate down, Greg and Joe, come and choose a secret frequency, and they set the clock to this 40 minus delta secret frequency, lock up the box, and go and take away their envelopes and try not to lose them. So they lose them. They kept the value secret until the analysis is complete. So we thought the analysis was complete a couple of weeks ago due to all the reviewing and everything else. And we met in Liverpool in the UK for our unblinding meeting. So here we are at that meeting. We're voting here. It's not an anonymous vote. We took photos of it. But here it is. We're voting there and on Zoom as well. And then here's me opening up the envelope to reveal the hidden frequency and the final result here, which I'll share with you now. So this is the starting point. This is how it looked at run 1, right? This is the same plot as before. We don't need all this other junk on there, so let's get to this point. So this is now our measured value here, right? So this was Brookhaven, and this is run 1. and then we're going to appear, down below, somewhere in here. Okay, so are you ready? We're here. Woo! Phew. So you can see, we all beat a very big sigh of relief when that happens. Woo-wee. So yeah, this is exactly, if you pick a point, you pick it. So we're just to the right of run one, very close, and same side as Brookhaven. So this is excellent agreement. The uncertainty on this one's halved to 215 parts per billion. Both our Fermilab results are statistically dominated. They've got basically the same systematics, and we understand them, so we assume they're correlated. And you end up with this final result for us. This is our combined now 2023 Fermilab number. It's got a precision of 203 parts per billion. Both of this and Brookhaven are also statistically dominated. We can combine those, and we end up now with a world average that's shown here, 190 parts per billion in there. But it's really starting now just to be dominated by the Fermilab result, right? You can see the world average and the Fermilab result here are very similar uncertainties, and they're very similar in mean as well. So as time goes on and these get smaller and smaller, it's just going to dominate even more and more. So I should have said, so on this plot here, right, one thing you can't see is that actually, kind of by luck, we ended up taking these measurements at pretty different magnetic fields, different in the scale of our experiment. They're very similar in terms of absolute scale. So what you can do instead is, so here's our new result here. So this is a plot where I'm showing magnetic field versus omega A, right? So, we've taken the ratio of these things, so it should be a straight line when you plot one against the other, and indeed it is. So our new results are here. In run one, we were kind of 14 ppm higher in the field. In Brookhaven, they happened to be just the other side, 14 ppm lower. And so you can plot this. You can see the points go through all nicely, and at the top, everything looks fine as well with A mu for all these different points. So this is just one of those real basic handles. It's a real sanity check, but it gives us some confidence to look, we can do this actually at slightly different magnetic fields and we get the same answer. We also checked against all sorts of other things, temperature, day, night, anything else we could think of, and didn't find anything that was statistically unusual. So we should take a look at the theory side of things. So as I mentioned before, the theory side is less clear than it was during run one. And so I've tried to put in some kind of artistic license here, and I've blurred this error band a little bit. So that's come over here to kind of show you that, this isn't such a hard cutoff anymore, maybe, and we're waiting. So there is still this large discrepancy between our result and the experiment. Right? We didn't move, and they didn't move because it's the same number. So we can then compare our significance, and we actually hit 5 sigma here between these two. So it's not quite time to pop the champagne yet, right? We expect this updated prediction, when it comes, is going to have more data in it. It's likely going to either increase the uncertainty or move over in this direction here, and it's going to yield a less significant discrepancy. But on its own, at the moment, we hit the 5 sigma here. You probably also want to ask me what the world average one is, so I'll put that on to save the question. So that's 5.1. Like I said before, Fermilab's dominating this so much that you get a tiny bit more, but we made it to 5 sigma without the world average. Now, why do I think, we talked before about why this is a bit blurry, but we can put the points on here. So one of the points that we mentioned before was this lattice point from BMW. So in this point here, I've taken the hadronic vacuum polarization out of the white paper result and then just substituted the BMW result in there. So it just goes here, right? So it's just the difference between these two is the difference between the HVP contributions. And sure enough, it falls in the middle, as you'd expect, right? If we instead play a different game with CMW, so this now follows what Alex was doing at Lattice 2023 on Friday. So in this, he did an analysis where he removed all of the data from below 1 GeV that went into this combination and just replaced it with CMD3. And then if you do that, then CMD3 was a lot to the right of the other points. It's a lot to the right over here and much closer to the experiment. Now, clearly, this one here is a pretty dubious point, and there's a lot of disclaimers from Alex's thing here, right? It's just cherry picking one experiment. I've thrown out 8 experiments and just put this one on here, but it's still useful to see it as kind of a bounding case about where it would land if CMD3 ended up being the definitive value in the end. One other note as well is SND2K was the other result. Just due to technicalities, you couldn't process it in the same way, but if we did, it would have ended up over here on this side of the plot as well. So looking at this, you kind of think, oh, there's work to do here, and there is indeed work to do. But there are many parallel efforts are underway on the theoretical side to resolve this ambiguity. There's all that extra data. There's a lot of work on the lattice QCD as well. So over the time scale of a few years, we will resolve this, I believe. Okay, so if you want more details, here's where you can find it. We've got a paper. We've submitted it to PRL today. It's going to come out in the archive tonight. You can get it now. If you can't wait till then at this link, you can just go to the G-2 webpage here at Fermilab and find it. And then we've also got an advanced draft of a PRD, a more detailed report here that we'll put out in a few weeks as well. So looking forward, where do we go here from here? Well, the future looks really bright. We've got a lot more data, as I said before. We've already beaten our systematics goal, and we expect to surpass our statistical goal once we've analyzed all the data. We are expecting theoretical improvements on a similar timescale to doing this analysis. 2025 is kind of what we're talking about here. But in the meantime as well, if you can't wait, do look out for some other analyses too. We also, as well as our main AMU measurement here, we've got electric dipole moment searches, CPT and LV Lorentz violation searches, muon philic dark matter searches as well. Right? And these papers will probably come out before the final result. Okay, so I'd just like to conclude then. So we've determined AMU to an unprecedented 203 ppb. This new result is in excellent agreement with run 1 and Brookhaven, and we more than halve the uncertainty from run 1. We've actually smashed our design goal with systematic uncertainty of 70 parts per billion, and the future is looking bright. There's lots more data to analyze, and we're going to squeeze the uncertainty down further in our future results. Thanks for listening.
So questions for James? You have to really move around because it's hard to see everybody. And you're not allowed to get coffee until you ask questions. All right, Peter.
So I'm obligated here to review the history of this a little bit. This experimental program started almost exactly 50 years ago when Vernon Hughes from Yale, my thesis advisor, saw the first CERN results and decided that can't we do that better? It took him the last 30 years of his life to make this happen. He was, I think, with no offense to Lee and others, the father of this enterprise. The ring that's out there now is the same ring that was at Brookhaven. Everything else is new. He would be smiling today, and Vernon didn't smile a hell of a lot. He would not have said, but would have thought, that the theory uncertainty is displeasing. It means physics conclusions are still hard to draw. On the other hand, that's a theoretical problem, and this is an experimental tour de force. You guys and girls should all be proud of yourselves. And finally, he would say, as he did in public over the initial Brookhaven results, as he beat into the heads of all 100 of his graduate students, including me, if it ain't 3 sigma, it's nothing to discuss. Well done, folks.
Get up, Pasha. Come on. Over there.
James, first, congrats to all of you.
Thank you.
And I'm sure you had more than one analysis going in parallel. What's the level of internal consistency between them?
Yeah, we certainly do, right? So I glossed over a lot of the details of the analysis here. So basically every number that goes in here is done by at least 2 people independently, right? We always want to make sure that on top of, just systematics, we don't just have a bug, silly bug, typo, that kind of thing, which goes. So every number that goes in here is done by 2. Some of them are done by a lot more. So the omega A analyses there's 7 different analyses going in there, done independently. And at the end, Well, they were all relatively blinded while we did them, software blinding. At the end, we do unblind. And they all agree within the expectation of, but they mostly use the same statistics. Depending on what you do, you use slightly different statistics depending on which technique you use. So there's some variation that comes from there. And then also some systematic choices as well. But, they agree at the level of, under 10 ppb when you really expect them to, and when there's different statistics, maybe it goes up to 20, 30, 40 ppb differences between them. But there's nothing that you wouldn't expect just from statistics alone.
BK.
You mentioned, it was a great presentation, James. Thank you. Congratulations to the team. You mentioned the future prospects for the Fermilab experiment. There's another experiment in Japan. They have their challenges. But can you just outline how the systematics of that experiment are different from this one? I mean, you've done a great job on showing you understand your systematics, but you study the things that you know. Maybe there's something you don't know, but just outline how the systematics are different from this measurement.
Yeah. Okay. Farah, can you go to 129? Yeah. Thanks. I've got a list there. I didn't remember this. So the JPOC experiment, I guess, is your kind of question here. So I can just sort of outline how that's different. So this is another experiment that's going to be measuring AMU the same way we have been here. And they're trying to do it in a different technique, again, to try and have different systematics and sort of check our experimental result, right? So the way it works, instead of injecting 3 GeV muons, high energy muons there, they're trying to inject very low energy muons in a high field magnet here without any electric fields, right? So for example, one of the main differences is there's no electric field correction because they're trying to limit all their electric fields. So that's our largest correction here. That's a kind of 300 ppb level. We think we're doing it right, but if we've messed that up somehow, then relations are all wrong and everything else, then this would be different. So in terms of how it works, the real challenge is cooling these muons down enough to then accelerate them up here to this 200 MeV level coming in here. What have I got on here? Yeah, so this is kind of what they were saying. So this is the muon beams accelerate from rest. There's no electric fields, and the magnet's just smaller overall, right? So it's much more easy to keep it uniform. I think they're aiming for a run comparable to run one result towards the end of the decade, right? So they're starting data taking 2028, I think is what they said to us. Is there still their aim? There's a lot going on, right? It's under construction. They've delivered the surface beam. They constructed the experimental area. They're taking data to demonstrate the muon cooling at the moment. So, it's kind of plodding on, and I think it's been a bit behind Comet in the past, but now it's coming to the forefront there. So yeah, that's the kind of status of it. But I think the main differences are, just one completely different detector, different technique, and the E-field is the main.
So could you show again the comparison with theory that?
That's 69 for?
Yeah. Then, so I think I said this on Friday, but I repeat it here. So I take issue with calling the hadronic vacuum polarization determined from hadronic cross-section standard model.
Okay.
Because it's considered that a logical possibility that there is new physics in the hadronic cross-sections, yes. So you are determining something that is not necessarily standard model.
Yeah, fine. No, I think that's a fair point, right? We're saying if these two numbers don't agree and everything is correct and there aren't any mistakes, then there's some new physics somewhere. So it's either in this number or it's in this number, right? And it could be there. And now lattice is in the middle, and so
So I'll ask about your experimental thing. I noticed that in your summary of systematics, there was a systematics for run 2-3, which wasn't considered for run 1. Can you tell us what it is?
Yes. I don't need a slide on it, I don't think. So that, yeah, that's this. Yeah, it's called, we can put it on, 54, please, for. So that's the differential decay effect, right? So that's this line here, right? It's very eagle-eyed. I'm trying to sneak it past you. You spoiled me. So this one here, right? So this was small. So the during run 1, we did know about this effect, right? So okay, so the effect itself is what happens when different muons with different momenta have different phases, right? And so if you have, for example, a correlation between phase and momentum that gets baked in the delivery ring, which is what we have. And so, you know, as you go around the delivery ring, some of those higher momentum ones spend more time in the bending magnets, so their spin rotates a bit more. And so there's a correlation there between phase and momentum. And then you put them inside our storage ring, and then the ones with higher momentum take longer to decay because they're more boosted, right? And so then over time, you're going to change from at the start when you had some phase, some average phase, and then over time, the ones with a different phase are decaying at different rates, and so you're going to change your phase over time, which is then a systematic, right? So we knew about the beamline one at run 1, and we evaluated that, and it's small, right? It was small and below our threshold for inclusion as a correction, right? And it was consistent with 0. We've now realized that there was another few other effects as well, which are a little bit larger. It's still, the value here is still consistent with 0, but we now make the correction. It's, I can't remember the number, 15 plus or minus 20 or something. So that's why it's ended up here as, oh, maybe it's less than plus or minus 20, plus or minus 10, 5 plus or minus 10, whatever it is. But that's why it's ended up in here now, but it was omitted in the previous one. We're improving all the time, and it was an omission in the last one.
So we just had a couple of questions from online that we wanted to go through. One got asked several times, so what's the plan for mu minus?
Okay, so yeah, we initially did have some plans to run mu minus, but that would have been in this run 6 here. But that didn't work out well with the accelerator campus and plans to get mu2e up and running as well. And so instead, we've taken more mu plus data and mostly concentrated on systematics this year as well. So we don't have any immediate plans to take any mu minus data.
Yeah, James, there's a question from online. It asks how many muons were in the ring at the start of the measurement and how wide was the beam in the radial direction?
I don't know, Briali. Yeah, so, oh geez, now you're asking me numbers on the spot here. So something like 5,000 muons at 30 microseconds or something like that. It's that sort of number. We see about 10% of them in the detectors. So, yeah, it's that kind of number, 5,000. And then the RMS is 18 millimeters in the radial direction, something like that.
And one more question before we go back to the room. What's the timeline of the next steps for the G-2's final analysis, theory advances, incorporating Novosibirsk data? And a related question asked, do we anticipate the improvements are going to be mainly statistical or systematic?
Yeah, so I'll answer from the experimental side first, right? So we've started analyzing this data now. Obviously, we're focused really heavily on analyzing this data for run 2, 3. But since we've been in the review process of that, we've really started ramping up 4, 5, 6 analysis. The target's 2025 at this point to have that done and dusted. It seems fine at the moment, right? But we'll see how that goes. In terms of the improvement there, the systematics are getting really hard to beat down much further. I think we will knock them down a little bit, provided we don't, discover something else about the way we ran the experiment slightly differently that inflates the systematics or anything. And I expect them to be the same or a little bit lower, and we're going to win statistically, right? We've got 4 times the data, the statistical error will halve again, and then we'll end up, 100 for the statistics. Oh, and theory-wise, yeah, there's a lovely talk by Ida in P5, which I would recommend you go and have a read of that. But there's lots of different things coming over, this year, next year, 2025. But there's a big sort of looming question mark over it all. If everything agrees and and it works, then by 2025, the theory uncertainties will be down really nice and small and everything else. But at this stage, where we've got these different values, it's hard to predict a sort of resolution for those at this point.
Great talk, James. Thanks. It's easy and fun to blame the theorists, but if you look at the dispersive measurements, they're sort of all over the place, and there's problems with Chloe and Babar and the CMD3 result. Muon E is supposed to address some of that.
Yep.
Can you say anything about how they're going to contribute?
Yeah, I can. Graziano, do you want to talk about Muon E? Oh. No, I can. Fine. Okay, so Muon E, yeah, it's a good question, Bob. So Muon E is a new experiment that's coming in. So instead of going in the instead of going in the space-like region doing the cross-section, instead it goes into a time-like. So instead of looking at E plus E minus dihadrons, they're actually looking more at muon electron scattering, right? And so the idea is to go, and there's test beams going on now at CERN, and to basically measure the really small angle of scattering really precisely and measure that distribution, and then turn that around into being a leading order calculation for HPP. So I think in terms of the prospects for it are really good. At the moment, it's kind of an early stage for it. I think it's kind of proof of principle and testing at this point. And then I don't know what the final time scale. Maybe short time scale.
I can just add that if we are approved, we next year, okay, we should submit a technical proposal. If we are approved, we foresee two steps. And the first step, which happens before 2026, so before the long shutdown 3 at CERN, we would like to measure the hadronic vacuum polarization a few percent level. This will be an important demonstration of the method. And after the long shutdown 3, we'll go for the final measurement at precision will be few per mil. So this is the plan.
Okay, so we want to thank the directorate again for buying coffee for us. So everybody, please come and join us for some coffee. And if anybody has any questions, feel free to come and ask us. And, you know, we'll be in the user center at 4 o'clock if you want to ask different questions when things been a little greased up. But thanks, James.